Hey, sorry about that. A little bit of technical difficulties with GoToWebinar there. Hello, everyone. My name is Aaron Stannard. I'm the founder and CEO of Petabridge. And today we're going to go ahead and talk a bit about one of the features of Akka.net that I think is really powerful and useful, which is our database agnostic event sourcing that you can get through Akka.Persistence. So the first thing we're going to talk a bit about today is we're going to cover Akka.Persistence real quickly. This is our event sourcing system that's built into Akka.net. Many of you who are joining are probably already using it to one degree or another. So we're not going to spend an enormous amount of time talking about it. What we are going to talk about, though, in the context of Akka.Persistence is how can you prepare yourself to actually leverage it for CQRS, being able to do Command Query Responsibility Segregation. So what this means in layman's terms is being able to take the event source that Akka.Persistence runs on top of and projecting it into read-friendly models. So you're going to see a little example of that today, where we're going to take Akka.Persistence data and then project it into entity framework tables behind the scenes. Next is Akka.Persistence.Query. This is our technology we're going to use to asynchronously create projections behind the scenes using all the previously event source data. We're going to talk a bit about what the different query types are and how we handle things like materialized views and error handling. That's all going to get covered. And then we'll talk very briefly about serialization and how to deal with versioning events and state, and also how to version your views while we're at it as well. That's like a concern you need to, honestly, like if you're trying to figure out how to handle versioning down the road, like after you've already gone to production with Akka.Persistence, we can still adapt to that and still support it, but it's a lot simpler if you have a plan ahead of time. We're not going to go into a giant amount of data on that because we have an entire hour-long YouTube video that covers it, but we will touch on it very briefly and talk about things like rematerializing. Okay, the first thing that we'll get into here is event sourcing. The whole idea behind event sourcing is basically kind of think of it like being able to compute the total balance of a bank account from the sum of all the debits and credits in the ledger. The implications of this for being able to apply that same model to, let's say, any business object inside your system is that all state is inherently self-auditing. I did some work with a customer in medical device sort of space a few weeks ago, and one of their big problems they have to deal with is Sarbanes-Oxley and other types of like SOC 2 compliance, that sort of thing. Auditing is a huge component of that. Having an event source kind of makes it so things can inherently be auditable out of the get-go. Compared to CRUD, event sourcing is like a quantum leap improvement from an audit standpoint. The other thing that's kind of important about the auditing facet of event sourcing is that in addition to telling you what changed, it can also explain why things changed. Your audit change log in a tool like SQL Server can't give you the why. It can only give you the what and the when, basically. The other things that are sort of significant about event sourcing is that state can be reverted and restored to a specific point in time. So if you think about, let's say, an object state, let's say the object could be an order, could be the status of a device if you're doing digital twins. It could be a transaction that's being executed through an OLTP system. The gist of this is that the current state that object's in at any given time is the sum of its events. It's a product, basically, a dot product of all the different events that belong to that individual entity. That means the way that state is represented can be set back in time if you need to. You can go ahead and pop events off of your event source and revert that object back to a prior state. This is really useful for doing things like if you work in finance, being able to back test a trading algorithm, or if you're working on more complex systems, being able to do regression testing or simulations. That's a really useful facet of event sourcing in its own right. Finally, the thing I find most useful about it is event sourcing is an inherently reversible architectural design. We have a video online, a couple of videos online and a blog post about high optionality architectures. Reversibility is a big component of that. That means that the way your state is represented, like in your application, that is a derivative of your event source at any given time. So if you don't like the way that state's represented, you can destroy it and then reproject your events into something else. The next thing I want to mention here is the way, kind of dovetailing with my last point, The current state you're looking at is decoupled from the data itself, like the way you represent data inside your actor or the way you represent data inside your read model. These are all derivative views of the underlying event store. That means that they can be destroyed and recomputed when your requirements change. So event sourcing lends itself very well to reversible decisions, which is great from a technical debt and from a speed perspective. Speed meaning how quickly your team can iterate on designs. There's a little bit more upfront engineering overhead to event sourcing initially, unless you're using a tool like Akka.Persistence, which we're going to talk about. But you get a lot of flexibility downstream as your domain inevitably evolves over time. And then the last thing we're going to talk about here is CQRS, projections, the ability to take our event store and reproject them into new forms. Akka.Persistence has been a part of Akka.net for 10 years, and it is a database agnostic persistence plus recovery mechanism for actors. It's designed to avoid lots of different potential problems that can happen in highly concurrent database intensive applications. A good example here is that Akka.Persistence inherently rate limits the number of actors that can recover their journal at any given time. The idea here is that, look, if you have 1,000 actors all trying to recover at once, that's going to go ahead and put a lot of contention pressure on the event journal. So we only limit by default 50 to recover at any given time. And that's actually going to improve the throughput of the application when we do that by constraining the degree of parallelism there. There's lots of other little things we do too to kind of help improve throughput and performance from a database perspective. We bound the number of open database connections that can be used at any given time. There's lots of multiplexing that can happen inside Akka.Persistence too to help reduce the number of round trips and that sort of thing. It's a very well-built, battle-tested piece of technology by this point. We use Akka.net serialization system to represent all of the events going into your event source for each of your entities as binary payloads. We do this because we already have to use Akka.net serialization for things like Akka.remote. So we just dovetail that into Akka.Persistence as well. This eliminates a really painful category of problem that a lot of hand-rolled event source systems have, which is dealing with how you version event schema, which means having to do, let's say, sparse tables in not Akka.Persistence, and doing it in SQL Server or another other types of databases as well. The way we handle this is we say, look, your database schema is basically never going to change. It's just going to be key value plus some timestamp data to help do ordering. And then it's going to be binary payloads with serializer metadata. All of the versioning of events and state is all things you can control through C# at that point. It's not a responsibility of the DBMS to do it anymore. And the trade-off there is that you actually get a high degree of flexibility as a programmer for dealing with things like versioning state, being able to go ahead and decide how you might want to change properties on events in the future. But the downside of it is that your data is not going to be human readable inside your event store. And by the way, that human readability component is what makes it so expensive to build an event source by hand in most systems. If you're trying to use, let's say, a native table schema to represent every possible event in your system, it's going to be problematic. What most people do if they hand roll a event source is use something like JSON anyway. So we're basically just doing that, but doing compressed binary instead. Finally, Akka.Persistence also supports Akka.Persistence.Query for doing projections. This can also work on pretty much any arbitrary database that we support. The way the Akka.Persistence runs, and I promise we'll see some code in just a moment here, the way Akka.Persistence runs is we have a persistent actor that's going to process messages, and these messages are going to produce events. These events represent state changes for this entity. So if I have a chat room history actor in this case, each one of these messages might represent someone writing to the chat room. I am going to persist these events into SQL Server, in this case, in the original order that those events occurred. When someone wants to communicate with this room message history actor, we are not talking to the database during read operations. This actor's state exists in memory, but it is also mirrored in a persistent, durable event journal that's, in this case, represented using SQL Server. The implication here is that we still get fast in-memory message processing with Akka.Persistence, but we also get durability and reentrancy. When this actor restarts, maybe it restarts because we killed the process and rebooted it, maybe it threw an exception and it got rebooted by Akka.net supervision system. Whatever the case may be, when this actor starts up, it's going to send its persistence ID to the Akka.Persistence journal actor. And that actor is going to figure out what are all the different events that this actor needs to replay in order to get caught up with its most recent state. And the actor will go ahead and replay all those events and rebuild its in-memory state, which it will begin using to process in-memory messages sent by other actors at that point. So that's kind of a brief recap on Akka.Persistence here. Let's take a little bit of a gander at the source code. The first thing we want to take a look at is in Akka.NET, persistent actors all need to have a globally unique persistence ID. No two actors talking to the same database can have or should have the same persistence ID. The journal in Akka.Persistence can usually detect when there's like two different copies of the same actor, the same persistence ID, talking to the same journal, and it'll throw a corruption exception when that happens. It can basically tell that you're corrupting your write layer when you do it. If you're planning on using Akka.NET and let's say a big distributed system and you want to help guarantee that all the entity IDs are unique, Akka.Cluster sharding is the right tool for doing that. It'll structurally guarantee that only one instance of this entity can exist anywhere in the cluster at any given time, even when there's network partitions. So we just released a video on that on our YouTube channel this week. Strongly recommend that you look at it if you want to know how that works. But for the time being, this is just an important constraint you need to know about with Akka.Persistence. This persistence ID is sacred. There can only be one of them in the entire system. That's only one instance of this persistence ID running at any given time. The next thing to learn about Akka.Persistence is we always try to recover a snapshot of our actor state first. Snapshots are kind of an optional feature of Akka.Persistence. You don't have to use it, and snapshots don't get used in projections. So for when we're dealing with CQRS, it's only the content, the event journal that we care about. But if you have, let's say, persistent actors that have been alive for a long time and have processed many events, you don't want that actor replaying, hundreds of thousands or millions of events each time it starts up. That might take hours to process, depending on how many of them there are. So what we try to do in order to accelerate Akka.Persistence actor recovery is that we have the actor periodically take point-in-time representations of its state, otherwise known as a snapshot. So the way Akka.Persistence works when recovering is we always recover the most recent snapshot, and then we recover any of the events that were recorded after that snapshot was taken. These recover methods inside this persistent actor right here, we have to finish fully recovering the actor's state before we're allowed to process messages from any other actors. If the actor can't finish recovering its state for some reason, let's say the database goes down in the middle of it, this actor will kill itself and you'll need to recreate it again. And that's because Akka.Persistence prioritizes data consistency over availability. So that's the trade-off we made. And the idea of a partial recovery is antithetical to the way Akka.Persistence works. We're going to kill ourselves if we can't recover. You should recreate the actor and then try again. And we have things like the back-off supervisor actor that can help automate some of that inside Akka.NET. Once recovery is complete, the actor begins working like normal. So that was kind of the read side of Akka.Persistence. Let's take a look at the write side of how we actually save events that we're going to recover and also replay for the purpose of creating projections. This is kind of following, if you attended my webinar that we did, I think last September on pattern-oriented design with actors, this is following that process here, where I receive a command, I basically have a little extension method that does all the processing on it, and that response I get back from this process command right here might include between 0 to n response events. If I have more than, let's say, 0 response events, I'm going to call persist all right here. This will cause me to persist all of the events that are in this an IEnumerable right here. This will cause me to replay all of them in order to, it will cause me to basically persist all of them in a single database transaction is what's going to happen. So they're all going to be saved atomically as one unit. Once that operation succeeds, we're going to invoke this little function for every single event individually that we just saved there. Now, one thing that's really important to note by default is this line right here. The actor won't process any messages until this persist all operation completes. This actor internally is going to use stashing and behavior switching kind of behind the scenes that basically make sure this actor can't process any messages until we know if this persist operation completes. You can disable that if you want to improve throughput. And the way you disable it is by calling persist or persist all async at the end of it. That'll cause the persist operation to basically complete in the background. And if you're okay kind of relaxing your consistency requirements in the name of reducing latency, that's how you can go and get around doing that. But by default, I'm just using persist all here. So this callback function will get invoked per event. Now, the last thing I kind of wanted to point out here is saving snapshots. What's sort of the right formula for doing that potentially? One of the things that I'm doing here is this last sequence number property. This is basically keeping track of the version of this actor state. The sequence number increments monotonically, meaning that it can only increment, it can never go down. It always increments every time I persist an event. So each event is basically identified in our Akka.Persistence journal using a tuple. On the one hand, we have the persistence ID. On the other hand, we have the sequence number starting from 0. So what I'm doing here is using a little bit of modulus to say every 10 events save a snapshot. And so when that snapshot successfully gets saved, that's going to go ahead and create a new point in time representation of our state. And we'll use that for recovering this actor the next time it starts. That way I can kind of constrain how many events does this actor replay any given time when I need to recreate it. I can limit it to, let's say in this case, 1 snapshot plus up to 10 events. So I'm never going to be recovering, let's say, thousands of events, that in one shot here. It's going to be a snapshot plus whatever this value is. That's a fairly healthy pattern for working with snapshots inside Akka.Persistence. Now, the way we configured Akka.Persistence, I'm using Akka.Hosting here, which I strongly recommend you use. We're using the brand new Akka.Persistence.SQL plugin that we shipped last summer. We're passing in a connection string, so that's normal. We're getting that out of app settings. We're basically specifying that we're using SQL Server 2019 here. This is using some of the linked DB settings. We're using the tag table. That's a more efficient way of querying events on secondary indices. We'll see an example of that in a moment. Then I'm also adding this thing called a write event adapter here. We will get into some detail on what that does in a moment. Now, messages as effect systems. This is from my presentation on pattern-oriented design we did last September, but I always organize my sort of message taxonomy into 3 components. Commands, which are inputs into a system, and when a command is successfully processed, that can produce between 0 and n events, or 0 and n effects. The events are the effects themselves. They're historical facts of the systems. Events really happened. So they can't be validated. You can't validate something that's already occurred. They can't be validated. They just need to be processed and incorporated into our state. And then finally, we have queries, which is basically the ability to fetch or subscribe to changes in state without actually impacting it directly. With Akka.Persistence, we are solely concerned with persisting events. And then if we're taking snapshots, persisting our state. We typically do not persist commands, nor do we persist queries. That's kind of not really useful unless you need it for auditing purposes. That would be the only exception where I might consider doing this. So event design. This is the section of the presentation where we're kind of thinking about how do we get ourselves ready to use Akka.Persistence effectively for CQRS. This is also from my sort of, my presentation I've been referencing a bit. I really like using these entity-specific interfaces where I have a unique key per entity here. And in this case, I'm using a string. This could also be a value object if you want to do that. It kind of depends on what floats your boat. But that's not kind of besides the point. What's really important is that every event that we're persisting has the globally unique identifier for it. Its primary key value is built directly into the event. I don't need to look up some synthetic table in order to do it. This will make doing projections a million times easier, and it's also good for a bunch of other Akka.NET specific reasons, such as you actually need this in order to work with Akka.NET cluster sharding, for instance. So this is a really good practice to get into. I also will use a separate interface to kind of separate events from commands or queries for this same entity type. And then finally, I have a concrete type here as well. One thing I mentioned is that order-dependent events are fine inside Akka.Persistence, meaning that if I have to have an entity receive a create event first before it's considered to be valid, and then afterwards that entity might receive other events that represent other incremental state changes, it's fine to have those ordering requirements. Akka.Persistence.Query by default works sequentially. So you're not really doing anything unusual there. That's kind of more of a problem that emerges in CRUD-based systems where you don't have control over the order in which things are done for specific entities very well. Akka.NET's mailbox system kind of forces you to do everything serially on a per entity basis anyway. And all the events are going to be persisted serially. They will also be replayed serially. So reasoning about order is actually very simple to do in Akka.NET because it's mostly automatic already. Now, as for designing your state objects, if you're taking snapshots, this is what I think works best, is immutable, simple, data-only types, meaning that your state does not necessarily have methods or other things that affect it. It's basically just a simple data object. Now, there might be situations where that a simple data object's not going to cut it for your actor state. I could definitely see some scenarios where that might be the case. In that case, what you might want to think about then is taking snapshots of your state using a data transfer object that is a simple data type, where you can go ahead and repopulate your more complex type using that DTO, and you can also easily convert that complex type into a DTO as well. That way, this is what's being represented in your data system, even if it is slightly different from the way your state is modeled inside your application. So that tends to be what I prefer here. Now, to prepare for CQRS, we want to think a little bit about the way in which entities are going to be queried downstream. How do you want to do projections? Do you want to do projections per entity? Meaning that, am I going to have a projector for every single entity that exists in my system? So this is supported out of the box. It's very easy for us to do. Each entity is going to be queried independently, which means we're going to have the maximum degree of parallelism possible inside our projection system. But it's going to put a lot more strain on the database if you have a really large number of entities. Like we did a blog post, I think, end of 2022, beginning of 2023, about how we introduced rate limiting inside Akka.Persistence.Query for SQL Server, because we were having users running, 4,000 or 5,000 parallel Akka.Persistence queries on every single node inside their network, which meant that every couple of seconds, you were having thousands of database connections getting open potentially. We've introduced a bunch of rate limiting features inside Akka.Persistence.Query that work pretty much the same way Akka.Persistence Recovery does. So you could have hundreds of thousands of queries running in parallel, and it's not going to tax the database. At any given time, only 50 might actually be connected to the DB. So you're not going to need to worry about connection pool saturation or other issues like that these days. So this strategy is totally supportable via Akka.NET's infrastructure, but it is going to be using more CPU, probably more IO, etc. But everything's going to be done at much lower latencies probably. The other strategy, which is what we're going to use inside this code sample we're about to look at, is one projector working across multiple entities. All entities are the same type, but it's only a single Akka.Persistence query. This typically relies on the tagging feature of Akka.Persistence. It is much less intense in terms of the amount of resources it uses, but it's much slower at producing projections. And the reason why is it has to work sequentially through the event store for all entities at any given time inside the system. So there's some downsides to it. Now, that being said, there's a lot you can do to potentially influence how quickly this thing works if you wanted to. But I think that this approach is generally the most cost-effective one. The other downside of this, I should point out, is that in extremely busy systems where you're writing, let's say, many thousands of events per second, it's possible that this query, because it kind of relies on polling the database, can miss events in extremely busy systems. Not very frequently, but it can happen. This is just a database kind of consistency issue to some extent. We're working on some fixes on a couple of different plugins for this right now. So for instance, there's a contributor working on using the MongoDB change feed to go ahead and power this in Mongo. That's an example of how we can make it more robust and not miss events. We're also looking at things like read behinds to try to make it easier to not miss these. This projection per entity approach relies on the sequence numbers, so it can detect gaps in queries automatically. This will never miss an event, but the tagging system might. So that's just a sort of, and by the way, when I say extremely busy systems, we're talking thousands of events per second usually. So Again, if you don't have that high of a traffic in your system, this will probably be fine. If you do have very high traffic, worth bearing in mind that this can happen. There's various tuning features available in the persistence plugins that can do things like change the read consistency levels to help fix this. But that being said, just wanted to make you aware there is a trade-off from a consistency standpoint with this approach versus this one. Nevertheless, this approach is what I'm going to be using today just because it's a lot simpler to demonstrate. Now, tagging events is a super useful feature. This is one of the big things that we incorporated into our Akka.Persistence SQL release. This is using what's called a I-write event adapter in Akka.Persistence. This is basically an aspect-oriented way of injecting additional data about each of the events we're persisting into the journal so they can be queried using additional indices, essentially. So by default, and I'll show you the table schema for the journal in just a moment, but by default, all events are essentially organized using the entity's persistence ID and its sequence number. This gives us another tag, another dimension by which we can go ahead and try to query events from across multiple entities typically. So if I have dozens of different types of entities all writing to the same event journal, these tags will allow me to go ahead and say, oh, get me the stream of all events of type product, or get me all the events of type sale, or give me all the events of type inventory change. That's what these tags will let us do here. So this little message tagger is something that gets configured when we set up the journal. And we're going to say, you know what, all the events that implement the iProduct event interface, we want to have the message tagger process those before they get persisted to Akka.Persistence. That way we can go ahead and enrich that data with some additional dimensions for indexing purposes. So that's what we're doing with this message tagger here. This is what's going to power our ability to query data across multiple disparate entities inside Akka.Persistence. Okay, now I guess the next thing we'll take a look at real quick is Akka.Persistence.Query. The idea behind Akka.Persistence.Query is that it is a streaming query, meaning that it runs either until it reaches the end of the stream, or it can run indefinitely until you shut the program down. So this events by persistence ID query is going to hit the event journal. This is what the event journal sort of schema looks like in SQL Server. We have an ordering value that's set by the database, the persistence ID, which is set by you, the sequence number, which is set by the persistent actor, and then the serializer ID and the manifest. This is the data that the Akka.NET serialization system uses to figure out how to deserialize this payload in the future. So what we're going to say here is if I want to query all events by persistence ID entity A, I'm going to fetch all the values where persistence ID equals this in their ascending sequence number order. So event 1, and then event 2, etc. And we will typically do this in batches of up to 100 events at a time. And we will stream the values using Akka streams to whatever the consumer of that stream is, typically known as a sink in Akka streams. That sink will go ahead and process those values. And every time we finish processing that data, we will go ahead and grab the next 100 chunks until we're caught up with the current state of that entity. Once we're caught up with the current state of that entity, by default, a perpetual Akka.Persistence query will pull the table for changes once every 3 to 5 seconds. That's a configurable value, but 5 is usually the default. There's several different flavors of Akka.Persistence query to be aware of. Any query that has the current prefix is a finite query. It'll get you caught up to the current representation of that entity or the current state of that tag, and then it'll finish once it reaches the very end of the process. Queries without the current prefix are infinite queries. They will not stop. They'll keep running indefinitely until you shut them down explicitly. So this is useful for being able to detect new events that haven't been written yet. So if you want to go ahead and constantly create new projections on the fly, which is what we're going to do in our code sample, you want to use the queries that do not have current in front of them. So we have events by persistent ID, get all of the events for a single entity. Events by tag, that's what we're going to use today. Get events from multiple entities that have the specific tag. All events, get everything in the entire journal for all entities. I do not recommend using this because you can end up getting a bunch of junk if you're not careful. And then finally, we also have a query for being able to learn about persistence IDs. As new entities are created, we can receive a notification about that the very first time they've been added to the journal. So that's another query type that we also support. Typically, the two big ones that most users use in practice are these two, the events by persistence ID and the events by tag. What the Akka.Persistence.Query engine will let us do is we get this continuous stream of events. So in this case, I'm actually using a little diagram from SDKbin 2.0, one of the products that we're building in-house here at Petabridge. And this is from our real sort of architecture diagram. Whenever someone uploads a package to our NuGet v3 API, we upload the package. We record an event that this package was uploaded into Akka.Persistence. We have a projector actor that's going to go ahead and tail all the events from Akka.Persistence. And based off the different package publish and update events, we're going to go ahead and update our little read model that actually powers all of the NuGet data feeds that people use to restore packages from SDKbin. So that's kind of an example of a read model design here, is that we're using Akka.Persistence.Query to update rows in like an entity framework table. The primary tool we use for doing this reliably over a long period of time are materialized view actors. This is just a type of actor design. It's not a base class or anything, but these are persistent actors who themselves are running Akka.Persistence.Query to basically project events from other actors. And the thing that they persist is their position in the data stream, known as an offset. So these actors will recover their offset position when they start. They'll resume their query from their last known offset, so they won't replay any events they've already successfully projected. And they're designed never to replay their own persistence activity. That's one of the reasons why we don't use the all events query, is because we would end up picking up our own persistence activity by accident in theory. So I'm going to go ahead and hop into a little demo here. This demo is available. Let me go ahead and pull up our browser. This demo is available as open source inside our Akka.NET Code Samples repository. If you scroll down here, you'll see there's 3 samples. This brand new one, event sourcing with CQRS and Akka.Persistence, and Akka.Persistence.Query. I have a little README here that kind of describes how it works and what we're trying to do. But without any further ado, let me go ahead and actually fire the sample up. I'm going to launch SQL Server real quickly. And that's going to go ahead and build my SQL Server image and try to migrate my entity framework schema onto it. Let me go ahead and do that. In fact, while I'm here, let me go ahead and get SQL Server Management Studio up and running, which should take hopefully just a second here. And let me go ahead and connect to here. All right. If I take a look at our Akka database, you can see there's an entity framework table, this dbo.products. This is going to be where our read models are stored. I'm going to open up Writer, and let me take a look at our solution real quick. We have 4 projects. We have our CQRS SQL Server front end, our back end project, and then we have our data model. Our data model is basically where our entity framework stuff lives. That's all that's in there. Our shared libraries where all of our messages and state objects and serializer stuff exists. That's actually, funnily enough, only used by the backend process. And then we have our front-end process right here, which is a really simple Blazor UI that uses no Akka.NET whatsoever. It only uses this SQL Server context that we're going to spin up. So let me go ahead and launch our Blazor front end. Okie doke. So we're using Mud Blazor, and right now you can see that there's 0 data inside the system. No Akka.NET code at all. I don't think this project even references Akka anywhere. In fact, let me just double check. If I take a look at dependencies, packages, yeah, just Mud Blazor and GitHub source link. Cool. So a pretty simple little front end project there. Now, if I fire up my back end project and I go down here, this backend project is going to use the exact same entity framework context that we currently have. And it's going to go ahead and use all the code we've previously seen. The only thing we haven't seen yet is this little bit of code right here, where we're actually starting our actors. We're going to start this little generic child per entity parent actor. This actor basically functions the same way Akka.cluster shard region would, just without sharding enabled. So it's doing more or less the same type of work. Then we have this little product totals actor right here, a basic persistent actor that's going to process these commands, persist them. We've already seen this code on the slides. Not doing anything all that spectacular here. Let me go ahead and fire up the backend actor, the backend process. And this backend process is going to use down here, it's going to use bogus to generate some fake data that should create some fake looking little products for us. And then we have our projector actor right here that we'll talk about in a minute. So let me fire up the backend. All right, so I can see a whole bunch of events getting processed. Let's see what's going on our front end. And lo and behold, I now have some data records available. So I think this thing will only produce maybe up to 100 products. Let's go ahead and flip this around. Let's see, what's our highest price product? Refined steel ball. What's the one we've made the most revenue from? That's going to change a little bit. And let's take a look at our back end. Looks like it is still processing some incoming events there. So we're still producing some stuff. We're kind of saving events sequentially. So that's all kind of happening using basically a bunch of asks internally. So that's still running here. And I think we should probably have reached the end of the event stream now. Yes, we have. Okay, so one thing that's worth bearing in mind, if I scroll up here, let's see, it looks like our projections finished at the very end down here. So you can see a whole bunch of logs coming from our projections. And if I go ahead and hit refresh on here, our data is done changing. So what's going on with our little read model here? How is all this working exactly? Well, if I go back to PowerPoint, actually, hold on a second. I'll discard my annotations for a moment. If we go back to our code, and let me pull up our actual projector code here. Product totals projector, here we go. Oh, sorry, this is it, our projector actor. Here's what this particular actor is doing. We are taking a service provider injected into our constructor using Akka.NET's DI system. And we have this materialized view state property right here that we're sticking basically as a property of this actor. What's going to end up happening is that this actor is going to recover its view state from the sum of all these different little events that we processed. Every time we successfully move through the event stream, we are going to update our materialized view state. So this allows the actor to basically pick up projecting exactly where it left off. One of the really cool implications of this is that this projector can actually run in a totally separate process from where all of your persistent actors are running. So the projector could be its own process in theory, if I wanted to. This projector, when it starts up, is going to remember exactly where it left off, and it's going to go ahead and replay all those events that it hasn't yet had a chance to project. I'm overriding this method right here, this on replay success method. This is a little piece of like actor sort of behavior that gets invoked when the actor is done recovering, but hasn't started processing any commands yet. So what I'm going to do here is call persistence.query.get and read journal for SQL read journal.identifier. Every single Akka.Persistence plugin we ship has some syntax equivalent of this. This allows us to basically just start reading directly from the journal for whatever our underlying implementation is. Like we have one of these for MongoDB, one for Azure Table Storage, etc. This is going to produce a Akka.stream source of type, I think it's going to produce the event envelope. Yes, that's what we're going to do. The sync in this case is going to be a sync actorref with ACK. This is basically a back pressure aware sync where you send this actor a message of a type event envelope every time a new piece of data arrives, and we need to receive this projection ACK message before we give the actor the next message to process. So this is basically how we make sure Akka.Persistence.Query gets back pressured when the actor is doing its projections. And finally, I create my actual projection right here. I do events by tag, and I pass in the tag we want to use, and I pass in our previous offset. This is what allows the query to basically reproject from its last known position in the stream. And this is going to cause it all to go ahead and begin running. And then down here, my actor is going to receive an event envelope. And every time we receive one of these iProduct events, I'm going to call this little try process method right here. And in the event that this try process method fails, We're going to do a little bit of exponential back off. That's kind of what this code does. But then if we succeed, we call persistent ACK. This is going to advance the stream forward. So let's take a look at persistent ACK real quick. I'm just going to go ahead and update my materialized view state. I'm going to persist my change in my view state. Every 10 events, I'm going to save a snapshot. And then I'm going to tell the sender, who's basically it's the Akka streams actor in this case, I'm going to tell it that we're ready for the next event right here. All right, all looks pretty good. Now, if I scroll back up to our try process event, this is where the actual projections happen. So let's go down here. This projection is this is why we passed in a service provider, by the way. Entity Framework by default is a scoped dependency. That's the lifetime it uses in Microsoft.extensions.di. So every time we work with it, we're going to go and create a brand new scope. So we create a scope that's going to give us access to the SQL Server context. We are going to dispose of it once this method exits. And depending on what type of event we received, I have a slightly different method for how we're doing the projection. So if I go down here, update our product definition, if we basically don't have a product definition, we will go ahead and add a new one and save those changes. I suppose I can make this do an upsert as well, that if we already had a product definition, I could attach it and change it, which is what I'm doing here for things like products sold. I'm going to go ahead and take the sold units and add the additional value that we received from this event right here. And we're going to update our total revenue. This is actually kind of a bit of an important trait, by the way, which is that you should have all the information you need in your event to be able to find the row in, let's say, your SQL projection that you're doing, or to find the key in a key value or document-based projection that you're doing. You don't want to have a bunch of crazy lookup tables and other junk like that when you're trying to do your projections. You want to try to keep things nice and linear, like how we're doing here. So we're using a really simple key system where we just look up the product ID in this table. We'll update some values, and then we'll go ahead and save that back using Entity Framework. And we do the same thing for this update product inventory right here. And that's basically the full extent of our projection process for this particular sample. Now, for larger systems where you have a lot more entities that all need to be processed and you're worried about basically this design being a little bit too slow, one thing you can do if you're able to relax some of your ordering requirements is you can either go ahead and pull more events all in one go. You can do that using Akka streams to specify it. And then you can have a projection actor per entity if you want to. That's particularly useful if you need to take one entity and project it into multiple different read models. If you're using, let's say, denormalization to try to optimize your read models for lots of different queries you might be supporting in your system. So a good example, if you have a pretty extensive reporting dashboard you need to support for one of your users, you might want to take events that are being produced by some of your entities and project them into all those different report structures that you need to support in your dashboard. You might want to have one actor that owns that for each individual entity inside your system. And in fact, that's actually what we go ahead and do for things like SDK bin behind the scenes. For every single product, and there might be dozens of products inside our system, they each get their own projection actor because they have to update a combination of, let's say, feed metadata, product utilization data, and license utilization data, all of which are different sort of domains in our system that all key off the same events to do different domain-specific things. So you can have an individual actor do that rather than having all that built directly into the projector itself. That's just a design decision. I kept this as simple as possible, mostly so you had one easy to kind of wrap your arms around code sample to look at for getting started doing this. Moving downfield to doing, let's say, an actor per, let's say, entity that manages all the different projections it does, that's a lot closer to what a real production grade system would probably look like, but we wanted to keep it simple for this sample here. So let me go and shut this down real quick. Okay, now going back to, I don't know why it keeps pulling up my cluster sharding presentation. Going back to this, thinking a bit about future proofing. And by the way, I've seen some folks writing some questions in chat. I'm going to get to those as soon as we are done with the presentation, which is probably about 5 minutes away from finishing. So let's talk a bit about future proofing. Extend-only design is something you've seen me talk about in our YouTube and in some of my conference presentations. It's also in the video that we're going to recommend on versioning state and messages. Extend-only design is the safest approach for versioning state and messages. It's even in the Google Protobuf documentation as the blessed way you're supposed to evolve your messages and events in Protobuf. We strongly recommend, once you start getting serious about using Akka.NET in production, schema-based serialization is probably the way to go, not reflection-based serialization. So Hyperion and Newtonsoft.json and even system.text.json are all reflection-based tools, ultimately. They have their purpose. They're very low total cost of ownership and easy to get up and running, but they don't support version tolerance inherently well. JSON is not a good fit for version tolerance. Protobuf is. That's one of the reasons why we strongly recommend it. This will save you a lot of pain and agony the earlier you adopt it. The other sort of things to bear in mind about extend-only design: we never rename, remove, or repurpose existing properties or types. You can always add new stuff. You can't get rid of or irrevocably change old things once they've been introduced. That's the whole point of extend-only design, is that once things are deployed, they're safe. They can stop getting used eventually once those features and functionality are deprecated, but you don't really want to go through and remove and refactor them. That's just going to inject risk, overhead, and complications into your system. And yeah, like you said, you can always extend what's there. You can always add new properties or new types. All new properties should be treated as optional and have safe defaults. So a good example in .NET parlance, all new properties should be nullable, meaning that basically they may not need to be populated. If you're replaying a older version of an event from your event store, it's not going to have properties that didn't exist at the time it was saved. Therefore, your code should sort of factor that into its design. It's not as hard as it looks. It's more of just like a habit you want to get into in order to make sure things are done safely over a long period of time in your software. From a versioning strategy standpoint, separating your wire types from your application types is one way of going about it. So define your wire types in Protobuf, have your application types defined in C# and F#. Maybe compress the number of unique wire types that you have. So these are the types being saved as records in Akka.Persistence. And then basically create an explicit serialization and mapping layer between the two. This is something that we cover in our video on how to do versioning. If you've been following some of our community stand-ups, you've seen a demo that Gregorius gave maybe about 6 months ago. We are planning on automating a lot of this stuff, so it's not nearly as much drudgery as it is today. So we are planning on making this easier in the future. Still a good idea to go ahead and try doing it on your own today. You will get a lot of benefit from it, both from a performance, a security, and a versioning sort of standpoint. A lot of good reasons to do it. You basically have to pay a little bit of overhead from a development engineering standpoint once, and it pays for itself very quickly, I promise. Now, the last thing I kind of want to touch on is changing the way you do read models, changing the way you project. One of the big things you want to bear in mind, I get asked sometimes about, let's say, storage costs when it comes to storing data in Akka.Persistence. If data storage is a problem, let's say if you're writing such a huge volume of events that it's going to start imposing like high costs on your database platform, there's a good solution for that, which is use a cheaper data store for right-side events. There's a reason why I like using Azure Table Storage as my default for most of these things. That's because data is dirt cheap on there, and all of Akka.Persistence queries work just fine. My read models that need to be cached and need to be included in maybe, let's say, joins and other sorts of reports or whatever, that can all live in SQL Azure if I'm deploying on Azure. But if I'm going to go ahead and basically have just my event store, which is primarily used for powering my actor state recovery and for powering my projections, you can just stick that in Azure Table Storage, no problem. So if you don't delete any of your events, you get a lot more flexibility and freedom with creating new read models later. If you go through and delete stuff that you might need, that's going to become a little problematic potentially for doing projections down the road. So this is a domain-specific thing you're going to need to consider in terms of how you deal with historical data. If you know for certain you're never going to need those events again because maybe your domain is highly perishable, then not a problem. You can go through and delete that. But if you might want that data for being able to do back testing or projections or whatever in the future, basically design it so your event store can just grow indefinitely and kind of plan for that in your infrastructure. That's why having a really cheap right side event store that's simple, like a key value system, is probably the way to go for that. Now, if you want to go ahead and add additional materialized views, there's a couple ways you can go about this. One is creating an additional materialized view actor that queries the exact same data, but has a different persistence ID, meaning that its offset isn't the same as the older persistent actor that had, basically if I go back to my source code here, this product projector actor, I can create a second one of these with a different persistence ID that queries the exact same events and updates totally different entity framework tables with it. That's a really easy way to create additional read models that didn't exist before. You just run those two projections in parallel. Doesn't cost that much. This will let you go ahead and easily add new projections if you want. The other thing you could potentially do is rerun a query. And by rerunning a query, here's what I mean. Go back to our source code. If I want to go ahead and rerun my projection, I can just change the persistence ID here, or I can go ahead and delete the most recent snapshot and all the events that belong to this persistence ID here. And this will cause this actor to rerun all of its projections all over again. That could be really useful in the event that, let's say, you aren't happy with your read models that you currently have and you want to redo all of them. Well, you can just go ahead and reproject them from scratch this way. The other thing that you might want to think about at the design of how you do your read models down below here is trying to make all of these operations idempotent. Update, all these different little entity framework updates we're doing. Most of these already are somewhat idempotent, although not really. Not with the way we're kind of computing these changes in inventory and revenue. That's not really idempotent. So if we end up reprocessing all of the events multiple times, these totals are going to get thrown off. So that's something you kind of want to be aware of. Is ideally you should try to model this idempotently. That gives you even more flexibility. But with like the types of reporting we're doing here, not really all that feasible. I would need to basically drop this table and rebuild it from scratch if I really wanted to fundamentally alter it in some significant way. And the thing that's cool about CQRS and Akka.Persistence.Query is it's very inexpensive to do that. So you have the freedom to do that without losing any business value. The reason being is that your events are your source of truth and they haven't been deleted yet. So that's the end of my presentation. Thank you very much for attending. I'm going to go ahead and answer a few questions that were left by members of the audience. But if you enjoyed this presentation today and you want some help figuring out how to get this type of CQRS design implemented in your own applications, please feel free to go ahead and contact us about a support plan. This is exactly the sort of thing that we do to help lots and lots of customers. So strongly recommend you take a look at that. You can go to pettibridge.com/services/support. And also, if you are a current support customer, we have Akka.Cluster sharding trainings next week, where we'll touch on how to deal with, let's say, the distribution of a lot of these entities across many nodes in the cluster. Now, that being said, let me go through my set of questions here and try to answer some of these. Okay. Let's see. Let's see. Chat, handout questions. There we go. Okay. All right. Okay, set priority. We'll go ahead and handle this question. Okay. The first question I have here is from, I don't know how to show these on screen, so I apologize, but I'm going to do my best to answer them. The first question I have here is from Richard Harding. What about any side effects, calls to other systems as a result of replaying events during recovery? That is a great question. You should not do side effects during recovery. What the right place to handle that, Richard, if I pull up my source code here to deal with a side effect after you're done recovering, would be if I go back to my product totals actor. Actually, I'll do it in my projector actor. The right place to deal with that is on replay success right here. This is sort of where you can go ahead and deal with side effects as you're done recovering. That's the right place to do it. The idea behind recovery is it's supposed to be quick and it's supposed to just get you back to your original state and not really meant to produce side effects. But you can do that in the on replay success right here. You could do things like inspect your current state and maybe change, I don't know, maybe you could potentially change the behavior your actor starts in, or maybe this can cause the actor to do things like, oh, I have a JWT that's been expired. I need to go get another one before I start processing messages. That's the sort of place where you might want to do that. Next question. Would you use an immutable state for the persistent actor even though message processing is thread safe? Doesn't it allocate a bunch of garbage in the process? In theory, yes. I like to use immutable state just because it allows me to model all of my transform functions as pure, which makes them really easy to test, and also has a couple of other benefits, such as being able to go ahead and repurpose them for things like simulations and that sort of stuff. The garbage collection overhead of modifying things like records is pretty negligible, to be honest, even if you had millions of actors all processing them at once. So I wouldn't get too worried about it. But if you did notice that start to become a bit of a performance concern, then maybe moving towards a mutable model might be better. The other reason why you kind of want to have an immutable representation of your actor state when you're saving it off for snapshots is if that state gets modified while it's being persisted, you can get some really brutal looking exceptions while that happens. Because technically the snapshot is actually being processed by another actor who is not you. It's happening asynchronously behind the scenes. So yeah, in hindsight, you really do need to make the snapshots immutable. So even if your actor state is mutable, whatever you send to be persisted, that does need to be immutable. Okay, question from Jason Petties. It was mentioned that the querying pulls data storage every 3 to 5 seconds. It seems like the queries could subscribe somehow to the persistence infrastructure to know automatically that new journal entries have been added without polling. Apparently, there's something wrong with that idea. Could you explain why Akka polls instead of tapping into Akka.Persistence to react instead of poll? Yes, I can explain that. We originally built Akka.Persistence to do this, in fact, and we had to get rid of it. The reason being for that is Akka.Persistence is distributed across multiple nodes in the cluster. If you have nodes A, B, C, and D, node A, even if it subscribes to basically node A's journal, won't be notified about events happening on journal D. So that's kind of what drives some of that functionality there. Now, what we could do potentially to try to make querying happen more efficiently, I guess, is we could have some way of, let's say, painting a query where we know that this query's been affected by something that happened locally on the node, and we can nudge it to go ahead and run now rather than 5 seconds. That is something we could in theory do. Probably the best compromise here is something like what we're trying to do with the MongoDB plugin, which is using things like the MongoDB change feed, where rather than polling for changes, we get actively notified about it. The biggest problem with like why we have to do polling is databases like SQL Server in theory support like just being able to subscribe to change notifications. I think it's the SQL Server service broker that lets you do that in SQL Server, but that feature isn't exposed on things like most editions of SQL Azure, for instance. So we can't really rely on that. And then other databases like Azure Table Storage don't expose anything like that at all. So the reason why the polling structure largely exists is mostly due to what the lowest common denominator of the database will actually support. Platforms that do support something at their sort of base tier that allows us to receive notifications about specific documents changing, that is something that we are interested in exploring, because that'll help get rid of this sort of like need to poll in the first place, and will help reduce latency and will help improve consistency as well, particularly for really high traffic systems. So that's why we do that. It kind of comes down to what does the ecosystem support. Next question from Mike. Does Akka.Persistence support event archival to keep the journal size in check and minimize indexing overhead? Will it start querying events from the sequence number stored in the latest snapshot? Yes, we do query events stored from the latest snapshot. The way to go ahead and do archival, well, in this case, we're not really doing archival so much as deletion, is that when we save a snapshot, I go ahead and I delete all the older messages and I delete all the older snapshots here. So I'm keeping the actor state compressed at any given time. In theory, you could go ahead and run an archival process and say, hey, go ahead and grab these ranges of data and move them into cold storage if you wanted to. Akka.Persistence probably won't ever support that right out of the gate because it's somewhat database specific how we would go about even doing that. But we do support things like being able to do sliding window deletions like this. Let's see, Malcolm. Can you speak how a database's change data capture functionality might alleviate the occasional issue of missed events when querying tags? Yes. So like I mentioned, MongoDB's change data feed functionality will do that. The reason being is I could basically subscribe to specific document indices and look for specific events that show up in there in order to use that to kind of drive the query forward. What that basically does, it kind of inverts the model from the client blindly querying the database to the database notifying the client when things are happening. That's sort of how it would alleviate that issue. So the problem is that because the client's polling and kind of guessing when things changed, that's when we might have, let's say, a section of rows in Akka.Persistence SQL, for instance, where we're typically doing, I think, is it read committed, I think is the normal consistency level we're using. It's potential there could be an uncommitted row sitting in the middle of that SQL Server just hasn't had time to process yet. And that's where events get missed typically, is through those sort of consistency problems like that. Well, if we're doing a change data capture feed and we're kind of working sequentially through all the different rows that are being committed, we can, as long as we can order that, then we're going to be able to go ahead and use that to basically make sure their cursor is kind of advancing sequentially. Now, if that didn't work for some reason, then we're kind of back to square one and looking at things like read behind mechanisms and doing trying to do gap detection and stuff like that. So these are all, let's say, like quasi database engineering sort of questions that we have to address, but hey, it affects real users, so that's why we invest time looking into it. Last two questions, both from Alex Baum. Is Akka.Persistence.Query the right tool to implement sagas and process managers? You could certainly do that with Akka.Persistence.Query, depending on, I guess, how you're looking for completion events. If you send a bunch of data off to entity actors and you want to use a query to verify they persisted the right event, you could definitely trigger a saga to do it that way. I tend to prefer in-memory messaging for sagas because I tend to want to have things talking. I want to have the saga talking directly to the actors doing the work. So rather than doing it indirectly through tailing events those actors are producing. So I probably wouldn't be my first inclination, but there's nothing wrong with doing it that way. Lastly, can I read the events of multiple tags to build a projection? Yes, absolutely, you can do that. You can do that using basically, if I go to my persistence syntax right here, what you could do is basically kick off multiple events by tag and then combine them into a single stream. That way the projector is seeing all the different events showing up. Now, if you're worried about debouncing or multiple events all showing up, you could use things like the group within stage and maybe do a little bit of sequence number or ordering ID filtering inside the stream graph here to eliminate duplicates where one event might show up in multiple tags potentially. Okay. I see a question here. This is a duplicate of a question that is on our Akka.net GitHub discussion thing. I will answer that question there. Last question, how hard is it to use Akka.net in an existing application? For instance, how to use it with custom DB context implementations? That is a good question and probably going to be the subject of one of our next webinars. I have it on my whiteboard actually as something that we need to do. It shouldn't be that hard. The first thing I wouldn't do if I wanted to introduce Akka.net into an existing app is I probably would not start using Akka.cluster and all the big distributed systems features. I would probably start by using actors to kind of do things in the background behind the scenes. So that might involve doing things like creating a simple persistent actor for keeping track of scheduled jobs, and then maybe using Akka.Persistence.Reminders to go ahead and execute them behind the scenes. Kind of think of that like a lightweight implementation of something like Quartz potentially. So there's a lot of different ways to get started of it. I don't think I can do justice to that on a quick Q&A here. Last question I'll go ahead and take is, does Akka.Persistence support sharded databases? If the database driver can support it, we can support it. So for instance, I know a few years back, we went ahead and modified the Redis plugin to support Redis clustering, which is their sharded implementation. And we know that the MongoDB plugin gets used with sharded Mongo instances quite a bit as well. So it definitely does support it. There's nothing explicit in any of the database drivers we use that would prevent that, I think. So I guess long and short, the answer to that question should be yes. Okay, well, thank you very much, everybody. I really appreciate your time and attention today. If you have any additional questions about anything you saw, please feel free to email us at hi@pettibridge.com, or you can also drop me a message in the Akka.net Discord. So thank you very much for your time today. Really appreciate it. And you should get a recording sent out to you later today. All right. Thank you very much.